Hey everyone, welcome to the lecture for section 5.2. We're going to talk about the uniform distribution. So the uniform distribution is a specific type of continuous probability function or continuous probability distribution, and it's concerned with events that are equally likely to occur. So every outcome is equally likely to occur when we're talking about a random variable that follows a uniform distribution. So when a random variable x, capital X, is known to follow a uniform distribution, we write x, and then this means similar. If you're typing in, say, like LaTeX, it would be the sim symbol, but I just say tilde. U for uniform, and then A and B. So A and B here are your start and end values. So A is the lowest possible outcome for X, and B is the highest possible outcome. So for example, I guess not example, in generality, the PDF for X, if X follows a uniform distribution on A to B, then the function is given as 1 over B minus A. And we define our PDF to be this height, this constant height whenever X is between A and B. And when X is outside of A and B, it's 0. So remember yesterday, or whenever you watched the 5.1 video, we talked about the area under the probability function, or the probability density function, or however we're calling it these days. This area has to be 1, right? So this is a really important characteristic for PDFs. So this area has to be 1. So when we're computing area, right? So if you're a little bit rusty on area, I would say that there's probably 3 general shapes that you need to know for chapter 5. One of them is rectangles, another is triangles, and the third is trapezoids. So if you're rusty on the area of rectangles, triangles, or trapezoids, definitely review those because you need them to compute area. So we're a rectangle today, which is great, nice and easy. So for a rectangle, we're just base times height. So our base here is B minus A, and our height here is 1 over B minus A. So this has area B minus A times 1 over B minus A. And so we see that these are going to cancel, and what we're left with is 1. Sometimes you're going to be given a uniform distribution, and you may be asked to determine what the height of the PDF is. Like, let's say it's from 5 to 10, what is the height going to be? We'll look at examples like that. The way that we'll compute that is just knowing the area is 1. So as promised in 5.1, we're dealing with continuous probability distributions that have known mean variance and standard deviation. So much like when we discussed the binomial distribution, we knew how to compute the mean variation and standard deviation just by a few key values, particularly n and p. Now, in order to compute the mean variance and standard deviation for a random variable that follows a uniform distribution, we just need to know A and B. And in fact, that's part of the reason why we write it like this. So think about this. We saw previously that X followed a binomial distribution with n and p. Well, guess what? Mu was equal to n times p. Variance was equal to npq, but q is just really 1 minus p. And then our standard deviation was the square root of this. So the only numbers that we needed to compute our mean, variance, and standard deviation, guess what? That's what's listed here. Notice that when we're looking at the uniform, in order to compute the mean, variance, and standard deviation, all I need are A and B. Well, guess what? That's what's listed here. So it should feel like we're listing the least amount of information needed to compute our measures of spread and center. So we have our formulas for mean, mu. So that's just A plus B over 2. And if I take A plus B over 2, that actually means that mu is going to be right down the center. So mu is right here. It's the midpoint of A and B. The variance is given as B minus A squared over 12. And the standard deviation, as always, oops, typo. The standard deviation, as always, is just the square root of that. All right, so now that we know the setup, let's try to answer some questions about a particular uniform distribution. So here in our example, we have people who follow a particular weight loss program lose between 6 and 15 pounds a month until they approach trim body weight. Let's suppose that weight loss is uniformly distributed. And we're given here that the random variable X is the weight loss in pounds for an individual in 1 month. So when we are working with a uniform distribution, we really need to know what our starting point and our ending point is. So it's going to be, because our random variable is the weight loss in pounds, it's going to be this 6 and 15. Okay, so what I want to do is, without worrying about whether or not this is to scale, I'm going to mark 6 and 15. And I know that this is where I'm going to have like the height of my PDF, right? So my PDF is going to look something like this, right? It's always a rectangle at a fixed height. So when I'm answering these questions for part A, I know that this is my A and this is my B. So I'm going to have 6 and 15 in my parentheses when I'm using this distribution notation here. Okay, so that has been done. Great. Now we want to define the PDF for X and graph it. And I think it's probably easier to graph it and then figure out what the PDF is, right? So we know that we're going to have this rectangular region. We know that it has to be between 6 and 15. And we need to know what this height is. So what is this height? Well, the way I'm going to find it out is that I'm going to use the fact that this area has to be equal to 1. So this area, which is base times height, has to equal 1. So the base, if I'm going from 6 to 15, that's a width of 9. So the way that you can compute that quickly, by the way, is that you would just say it's 15 minus 6. That's how we compute distance between two things. So I've got 9 for my base. I don't know what my height is, and I know that when I multiply them together, I'm going to get 1. So let's divide each side by 9. And here I have h equals 1 over 9. So that tells me that this height is 1 over 9. So if I wanted to state the PDF for this, I would say that f of x equals 1 over 9, just a constant horizontal line, for x between 6 and 15. So I can write that as an inequality. And it's always 0 otherwise. So again, what that means is that whenever I'm between 6 and 15, I've got this rectangular block above me that's giving me a probability. Whenever I'm outside that, I'm a flat line over here. And we know that a flat line, because probability is given by height, this flat line on the axis itself has 0 height, therefore 0 probability. So that's where I'm writing f of x equals 0. So next I want to compute the mean, the variance, and the standard deviation. So let's recall mean, variance, and standard deviation are all given at the top of the screen. So I've got mean is the halfway point. So it's a plus b over 2, or the midpoint. My variance, sigma squared, is b minus a squared. So b minus a is just the width. And then for the standard deviation, I'm just going to take the square root of that. So if I take the square root of that, you could cancel the b minus a squared bit and then just have root 12 on the bottom, or simplify that further. Go nuts on that if you want to. I'm going to leave it as the book gives it. I think it's easier to remember. All right, so let's compute it. We know that a is 6 and b is 15. So for mu, I get 6 plus 15 over 2. So that gives me 21 over 2. So that's going to give me 10.5. So notice that 10.5 is right in the middle. I want to kind of, maybe we could look at this a second time. Right, so where does 10.5 fall in between here? So remember that the distance between, the total distance was 9. So 4.5 is halfway. 4.5 is half of 9. So we can see here definitively that the mean is right in the middle of our uniform distribution, and that's always the case. So here's mu, and it equals 10.5, right? So if I go 4.5, if I'm at 6 and I go 4.5 to the right, that's going to put me at 10.5. And then if I go another 4.5 to the right, that's going to put me at 15. So we can see that the mean here is the midpoint between A and B. And as always, think of the mean as splitting up stuff in half in some sort of sense. Next, we want to compute the standard deviation. So we're just going to follow our formula. We have sigma squared equals b minus a. So that's 15 minus 6 squared over 12. So that's 9 squared over 12, 81 over 12. So as a reduced fraction, 27 over 4. As a decimal, 6.75. And then I'm going to compute the standard deviation by just taking the square root of this. So this is going to be the square root of 6.75. Or I could say the square root of 27 over 4. So if I take the square root of 6.75, $2.59807, right? So we can round that to whatever. Let's say we want to round it to the second place. So that's going to give me 2.60. So if I wanted to move one standard deviation to the right of the mean, that would mean you're at the mean and then you would go over one standard deviation, which is 2.6. So this distance is 2.6. So if I'm already at 10.5 and I go over 2.6, then that's going to put me at 13.1. And if I go one standard deviation below the mean, I'm going to go to the left 2.6. So I'm going to take 10.5 and I'm going to subtract 2.6. And so that will put me at 7.9. So here I would say this blue area represents all of the data that's within one standard deviation of the mean. This is a common idea that we're going to see a lot in chapter 6 in general. So start thinking about that a little bit. Let that marinate between your ears. All right, so next we're going to compute the probability that x is greater than 12. So the key thing here to remember is that probability equals area. That is the big takeaway. So probability equals area. All right, so if I want to look at greater than 12, so that's going to be, let's say here. And so the probability that x is greater than 12, so remember that this is the same as writing x greater than or equal to 12, because that single point of 12 has no width, and probability of a single value happening is 0 when you have a continuous distribution or a continuous random variable. All right, so I'm just going to leave it as whatever, pick your poison. I'm leaving it as the first one. It's equal to this area here. So what is this area? So the area of this shaded region is, well, from 12 to 15, this is a base of 3, and the height is always 1/9, always, always. So this is just 3 times 1/9. That gives me 3/9, or I could reduce and write it as 1/3. So the probability that x is greater than 12 is 1/3. All right, let's compute the probability that x is less than 9. So let's say 9 is here. So now I'm looking at this area right here. So we're in the same boat. We've got a base of 3. We've got a height always of 1/9. That's never going to change. And so our probability that x is less than 9 is the same thing as this area right here. So we just need to compute this area. Again, it's 3 times 1/9, which is going to be 3/9, or 1/3. If I want to compute probability between two values, it's as simple as just marking off where those values are, kind of determining what my region is, right? So if this is 9 and this is 12, I'm looking at this region here. So the probability that x is between 9 and 12, well, that's just the area of this region. And guess what? It's also 1/3. So these 3 problems right here, they just broke apart our total region under the rectangle, or in the rectangle, into chunks of 3. So I'm going to have 3 times 1/9, base times height, give me 3/9 again, 1/3. All right, now let's look at a conditional. So conditional is where we really struggled. Compute the probability that x is less than 8.2, given that it's greater than 7. So remember, the probability of A given B is the probability of A and B, the probability that both things are true or both things occur, divided by the probability of A. All right, so what are we given? We're given that it's greater than 7. So this is our given. So B is our given. And you know what? I wrote down my formula wrong. There we go. This should be B. So I want to find, let's convert this into the context of the problem. So I want to find the probability that X is less than 8.2, given that X is greater than 7. So let's look at where 7 is. So let's mark off 7 and 8.2 while we're here. Not to scale, don't care. So let's start with the given condition. X is greater than 7. I'm going to shade that with yellow. So this yellow region represents X is greater than 7. And I also want to know X is less than 8.2. So I'm going to shade that region with blue. All right, so now I want to look for my numerator. I'm looking at the probability that X is less than 8.2 and X is greater than 7. So that's going to be where both A and B are true, right? So we've got A and B. So we know that when we're looking at these and probabilities, we're looking at the intersection. This green region, this is the probability that X is less than 8.2 and X is greater than 7. So now we have to convert that into a number, right? But we know that probability is just equal to area. So the width I have here is 1.2. So this equals 1.2 times the height, and the height is always 1/9. So if I put that in my calculator, 1.2 times 1/9, I get 0.13 repeating. Or I could write this as 2/15. The next thing I have to look up is the probability that X is greater than 7, because that's my denominator, the probability of the given condition. So the probability that X is greater than 7, that's going to be, right, from 7 to 15, so that's 8. And my height is always 1/9. So the probability that X is greater than 7 is 8 times 1.9. And so that gives me 50. Wow, sorry, 1/9. So that gives me 8/9, or I could write 0.8 repeating. All right. So now what's going to happen is, now that I have my probabilities, I can go ahead and put them into the ratio, right? So the probability that X is less than 8.2 and X is greater than 7, again, that's that green region of overlap. And we saw that that was 2/15. So I have 2/15. The probability that X is greater than 7 is the yellow region, right? So that's from 7 to 15, and that's going to be 8/9. And so I'm going to do keep change flip 2/15. change, flip. And I can cancel out a few things here. So for example, I can take the 2 and the 8 and make it a 1 and a 4. And I can take the 9, pull out a 3, and take the 15 and pull out a 3. So that's going to give me 3 out of 20. Or you might have used your decimals and you should have gotten 0.15. So that is the probability that x is less than 8.2, given that it's greater than 7. Let's try another conditional probability. Compute the probability that x is greater than 10, given that it's greater than 8. So I need to mark off 8, again, not to scale, and 10. So given that it's greater than 8, that's going to be this yellow region here. And then probability that x is greater than 10, that's going to be this bit right here. And we can see that the intersection contains all of x greater than 10. So again, the probability that x is greater than 10, given that x is greater than 8, equals the probability that x is greater than 10 and x is greater than 8, divided by the probability that x is greater than 8. So let's start with x greater than 8. X greater than 8 is just the yellow region. So the yellow region has base 7, height 1/9. So I have something over 7/9. All right, and I need to know the probability that x is bigger than 10 and x is bigger than 8. So that's where I'm going to have my blue shade and my yellow. So notice that the blue and yellow combine to make green. So I'm really looking at that green region. So the green region has width 5, height 1/9. So the probability that x is greater than 8 and x is greater than 10 equals 5 times 1/9, which equals 5/9. So I'm going to keep change flip 5/9 times 9/7. Definitely going to cancel out these 9s. And I get 5/7 as my answer. All right, so now we kind of have a trickier question. We're given that x follows a uniform distribution on 2 to 5, and we know that the probability of x being greater than some value c is equal to 0.25, and we want to know what c is. So let's graph this out really quick. So I'm uniform on 2 to 5. So the first thing I need to do is I need to figure out what my height is. So remember that f of x is equal to 1 over b minus a. So b minus a is 5 minus 2, so I'm going to get 1/3. That's one way to do it. The other way we've been doing it is we're like, oh, this is 3. So I need to figure out what to multiply by 3 in order to get 1. All right. So now we need to figure out where this C value is. So first of all, I'm looking at X greater than C. So that means I'm looking to the right. So if this is C, I want this area to be 0.25. And now I just need to find C. So what is the area of this region? Well, it's going to be base times height. Our base here is 5 minus C. Our height is 1/3. So this area, we've got the probability that X is greater than C. I know it's equal to 0.25, but I also know it's equal to this area. So I get 5 minus C times 1/3 equals 0.25. And so now what I want to do is I just want to solve this for C. So the first thing I'm going to do is I'm going to multiply by 3 to clear out this 1/3. Or you can think about it as dividing by 1/3. So I'm going to have 5 minus C equals 0.75. And now I'm going to solve for C. So I'm going to subtract 5 from each side. So I get negative C equals negative 4.25. And then I'm going to divide each side by -1 to clear out the negatives. And I get that C equals 4.25. So let's actually test that out a little bit. If C is really 4.25, as we suspect, if this is really 4.25, then this distance is really 0.75. And so 0.75 times 1/3 equals 0.25. So that checks out. All right, next, suppose again that X is uniformly distributed with the following PDF, right? So what this graph is telling us is that it's uniformly distributed on 4 to 12. So this is saying just kidding. This is saying that X follows a uniform distribution on 4 to 12. And if that's the case, then the height, right, 1 over B minus A is going to be 1 over, well, B is 12, A is 4. So that's going to give us 8. So this is 1 over 8. So now I want to figure out what is the probability that X is less than or equal to 5 or that it's greater than or equal to 8. So here's 5. And let's see. Maybe I'll color code this a little bit. And where would 8 be? So 8 would probably be, oh, that's terrible. There we are. 8's in the middle. So when we did probabilities involving OR in chapters 3 and a little bit maybe in chapter 4, we had to add them up separately and then subtract their intersection. But here we actually don't have any intersection. So we're just going to add up these two areas separately. So this area, this is 1 times 1 over 8, which equals 1 over 8. Remember, OR gets that plus. So I have 1 over 8 plus, and then this area here, this is 4 times 1 over 8, which equals 4 over 8. I'm going to leave it as 4 over 8 just so I can easily combine these fractions. But notice that it's 1/2, right? Well, of course it's 1/2 because 8 is the mean. It's the midpoint between 4 and 12. So we know that half the area lies to the right and half the area lies to the left. All right, so I'm just going to add these up together. 5/8. This is my answer. Just added up the areas separately. All right, so we have 2 more questions. So we're going to have the same probability distribution. Oh no, just kidding, a little bit different. So now we have a uniform on 2 to 6. So notice that this is going to be one-fourth, or you could write 0.25. So now I want to look at the probability that x is less than 4, given that it's less than 5. So 4 is here, 5 is here. So this is going to be probability that x is less than or equal to 4, given that x is less than or equal to 5. So as a fraction, I'm looking at where both things are true. X is less than or equal to 4 and x is less than or equal to 5. And then I'm going to divide that by the probability that x is less than or equal to 5. So let's start with the numerator. X is less than or equal to 5. What is the area of this region here? So I'm going from 2 to 5, so my base is 3. Where should I put this? My base is 3 and my height is 1/4. So it's 3 over 4. So the next thing I need to do is I need to look at the probability that x is less than or equal to 4 and x is less than or equal to 5. So in order to do that, I'm going to shade where x is less than or equal to 4. I'm going to shade a little bit outside the lines just so we're clear that it's not green, it's blue, and that it's an intersection. So I'm looking here. And this area has base 2, height 1/4. So that's going to give me 2 over 4, or 1/2. So now that I have my probabilities, I'm ready to go. I'm going to plug them in. So this equals 1/2 divided by 3/4. So that's 1 over 2 times 4 over 3. So I can cancel out this 2 and this 4. And this gives me 2/3. But this makes sense actually, because if I look at this, if I were to put another split right here at 3, I would notice that if yellow is my denominator, there's 3 equal sized chunks. And the numerator is the top, and there's 2 equal sized chunks, so 2 out of 3. So intuitively, I'm hoping this is starting to make a little more sense with conditional probability. For this example, I'm going to make a quick edit. I just want to answer the first part. What proportion of values are within one standard deviation of the mean? So in order to do this, I need to know the mean and I need to know the standard deviation. So the mean is just a plus b over 2. So let's notice here that we're given that x follows a uniform distribution on 2 to 6. So that's my a and my b, that 2 and that 6. So I'm going to have 2 plus 6 over 2. So that's going to give me 8 over 2, which is 4. So now I have my mean is 4. Right, that's the midpoint between 2 and 6. Then my standard deviation is going to be the square root of 6 minus 2 squared over 12. So this is going to give me the square root of 4 squared over 12. And so if you put this in our calculator, yes, you can simplify it if you want to. I'm just going to give us a decimal. So I get 1.15 approximately. So I want to know what proportion of values are within one standard deviation of the mean. So I want to do, so this is mu. And if I go one standard deviation over, this will be mu plus sigma, right? I'm adding a standard deviation to the right. And I'm also going to add a standard deviation to the left. So that's going to be mu minus sigma. And I want to know what these values are so that I can compute the area. So here we see that mu plus sigma is 4 plus 1.15. And mu minus sigma is 4 minus 1.15. So that's going to give me 5.15, and this is going to give me 3.85. So now what I want is I want to compute this area here. So this area, if I wanted to look at the shaded area, right? It's going from 3.85 to 5.15. So the base is 5.15 minus 3.85, right? That's how we find the distance between things. It's also 2 times the standard deviation, by the way. So the base is 2.30. And the height, we didn't really get to that, right? We don't have the height yet, but we do know that it's uniform on 2 to 6. So the height is going to be, right? We always know that we have this. So the height is 1/4, right? It's just whatever value of f of x. So now in order to compute this area, I'm going to have 2.3 times 1/4. And I get 0.575. So what proportion of values are within one standard deviation of the mean? The answer is 0.575, right, is the proportion of values that are within one standard deviation of the mean.